Should I take that?
Right. Hello, my name's Alex Mottram, and this is Alex Ramadan, this is Kirsty Roy, and we're here from the CPE today to say why we are the force for change, unlike any other machines indoors or anything like that. So first of all, what is plastic electronics? Now, what plastic electronics is really simple. It's merely starting to use organic materials within electronic devices. But what's more important is what that means about the electronic devices you can make. So if we use plastic or organic materials, whether they be small molecules or whether they be polymers, it means we can make devices that could instead be flexible, they could be transparent, they could be more robust, they could be cheaper, and anything like that. It also changes the manufacturing processes we use, and that's what I'm going to talk about next. So the best way to consider plastic electronics is to see how it's different to conventional electronics. Now, conventional electronics is based upon silicon and metals, and you control the properties of your devices by using doping or different device structures, and that's about it. You produce your conventional electronics using lithography, which is peeling back layer by layer till you get the device you want to make. When it comes to plastic electronics, we can control our structures by using different chemicals, different chemical structures, and how those chemicals compact and react together. This means we can make them in different ways as well. And the ways we make them are far more scalable than conventional electronics. So if you're in a lab, you can start off with some really simple process just by spin coating it on, or you can basically spray paint some of it on. If you want to then move up to something a bit more complex and a bit faster, you could get an inkjet printer, especially made for plastic electronics, of course, and you can print on with this inkjet printer. Then you could go on to, say, wanting to make mass manufactured electronics, and you could get roll-to-roll printing similar to that used in the newspaper industry. And this means that we can have these faster, more robust devices that are potentially cheaper and flexible. So, what's most important, though, is how plastic electronics is going to heal the world. The world has problems. We all know this. We all know that energy is running out. Energy is running out. We don't have enough energy, and we need to think of new solutions to control our energy use. And one of them could be plastic electronics. Also, we've got an aging population, and we need new treatments and methods of dealing with old people. Next, we've got displays. Now, I'm sure everyone's used to having the black and white TV in their room, or maybe not so anymore. We're more demanding about what we want from our visual displays, and so we want better displays and bigger displays. And finally, lighting. I'm not sure how many people who've lived in a basement flat, but the lighting in your flat is very important. The colour of that lighting, the perceived colour balance of the lighting is also important. So we think, and I'm going to pass you to Alex Ramadan to explain why plastic electronics can solve some of these issues.
So I just thought I'd give you a brief overview about the devices in plastic electronics. So there's four main types. You've got the organic light-emitting diode, you've got the organic photovoltaic, you've got the organic field effect transistor, and the organic photodiode. So the organic LED was the first to be introduced to the market because it was the first to be developed. If any of you have got a Samsung Galaxy phone or tablet, then you own technology which uses OLEDs. In addition to this, Samsung are bringing out an OLED TV, which hopefully should give some better display quality. Philips have developed OLED lighting, which you can see here, which hopefully will be entering the market soon. And the good thing about OLED lighting, it's tunable, so you can choose what shade white you want. Even the fashion industry decided to take note. You've got Fergie from the Black Eyed Peas here, wearing an OLED catsuit. I think that's pretty cool. So one of potentially the most promising parts about plastic electronics is that you have organic photovoltaics or solar cells. And so hopefully we can go some way towards solving the world's energy crisis. They're flexible, they can be transparent, and they're printable, which is what makes them a really promising alternative to conventional silicon technologies. Also, for countries that don't possess the really expensive processing plants required for silicon-based technologies, OPV is a really good alternative because you can just print out solar cells and just go. So here we've got a very classy organic photovoltaic bag. You can charge your iPhone or your phone up on the go. In California, bus stops have started to introduce organic photovoltaics to power their lighting and their adverts. You might notice I'm using a bit of a different laser pointer. This laser pointer uses organic photovoltaics to power it. Pretty good. So the other technologies in plastic electronics, you've got the transistor. Now, it's a slightly less mature technology than the OLED or the OPDs, but it still shows a lot of promise. Here, Plastic Logic have developed the first colour flexible electrophoretic display. So you can have a Kindle that you can roll up and that would be colour. We've got Sony who've developed the first fully plastic electronic device. You've got OLEDs and OFETs using it. If you, say, live in a high-rise building and you want a really big TV, this is good news for you, because you can just roll up your TV and shove it in the lift. In terms of healthcare, plastic electronics can also play a big part. We can use plastic electronic devices and sensors, or here we've got a catheter for heart surgery, and even here, the OLEDs can be used for the treatment of skin cancer. So it's all really promising, basically, and these are just a few examples of how plastic electronics can be used. Now, this all sounds really great, but obviously we wouldn't be here if it was all perfect. So there's still a lot of work to be done. For a start, the printing technology that we really want to use is not common enough to be able to bust out for mass production. The physics and chemistry behind devices is not fully understood. And also, the device stability could be better. And that's where we come in.
Okay, so we've put together a family tree of our DTC, so all the cohorts together. There are 4 cohorts so far. And this is really just to demonstrate the scope of our research and how we contribute towards this plastic electronics community. So you can see we have a few groups working on the synthesis of new organic materials. These work alongside the material scientists and the physicists, who also work closely with the device engineers. Aren't we an attractive bunch? So here we just have a couple of examples of the work going on within the DTC. So Abby Casey is a synthetic chemist, and she's working on developing light-absorbing donors. So these materials are small molecules that are used, that are solution processable, that are used in our OPVs. We also have Sheridan Few, who's working on modelling charge transport for organic solar cells. He's part of a larger community within physics, which look at the fundamentals of these materials so we can better understand how they work. This is a bit mucked up, but we also have Joe Shaw, who's looking at novel patterning and has developed so far a technique which uses a heated tip to pattern these organic materials on a nanoscale. And you can see that he's created this replica of the CP logo. We've got George and others who are working on hybrid organic light-emitting diodes, looking at novel device architectures to improve the efficiency of these devices. So far, some of our research has attracted some prizes and additional funding, which is always useful. So specifically, David Beasley here, he's recently won a prize, the EPSRC ICT Pioneer Competition, for his novel technique for patterning electronics on nanoscale. We also have James Bannock, who works on the synthesis of P3HT, one of the polymers used in our OPVs, in a droplet-based microreactor. This is particularly interesting, and this is his setup here in this video, because unlike traditional batch chemistry, this is a continuous flow. So it's very suitable for large-scale production of these polymers, which industry requires. And for that reason, it's attracted some industrial interest. So Solarpress are currently using his material that he has made. And it's currently in production in their OPVs on their roll-to-roll systems. Yeah. Not only have we been successful academically, we've also done a lot of outreach work. So we've either gone into schools or schools have come to us, and we've tried to explain our research and the concepts behind it to sixth form age children. We've also had recently a stall with the Institute of Physics at the Big Bang Fair in London to try and explain some of our concepts to the wider community as well. So, on that note, we believe our research is great and we have a lot of fun doing it.
I can say that in time. Did you listen for later?